Okay, moving along. Okay, we have what will be regarded as orthogonal sets, and we have, by definition, a set of vectors ranging from v of 1 to v of p is said to be an orthogonal set if each distinct pair of vectors from the set is orthogonal. That is where you can have any distinct pair, and where if you take the dot product, the result will end up as 0. And okay, now we have just examples of determining whether a given set of vectors will be orthogonal or not. Okay, let's say we have with the given trio in the first case, we have v of 1 to consist of 2, -7, -1. v of 2 we have at -6, -3, 9. And v of 3 we have at 3, 1, and -1. And to see if these 3x1 vectors will form an orthogonal set, okay, so we'll be looking at the combinations to see if the dot products will be 0 throughout. And so we have between v of 1 and v of 2, again, just going back to the previous section, we can take the transverse of the first vector multiplied by the second, and the result is 0. Okay, so far so good. Now we have another combination we have between v of 1 and v of 3, and here again you have the transverse of v of 1 multiplied by v of 3. Okay, so you have 3 times 2, 1 times -7, -1 times -1, and the sum of the products we have at 0. And now, so you have v of 1 mapped with v of 2 and also with v of 3, and the remaining combination we have between v of 2 and v of 3. And so for what we have in setting up what we have and attaining the dot product, it turns out that for the elements that correspond, you have 3 times -6, 1 times -3, and -1 times 9. However, the sum of the products, instead of being 0, would come out to -30. And since we do not have all the dot products to end up as 0, it turns out that for this particular set, okay, it is not orthogonal. All right, now if we move on to the next set, and we have for v of 1, v of 2, and v of 3, okay, these are 4x1 matrices. And now in looking at the dot products, okay, and you can just run it through the mill between v of 1 and v of 2, v of 1 and v of 3, as well as v of 2 and v of 3. It's going to turn out that all the dot products will be 0, and this particular set is going to be orthogonal. Now, in the case of what we have among orthogonal sets, okay, we have what would be regarded as combinations within the subspace, okay, where we have an orthogonal basis. All right, and we have an orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set. For each linear combination Y in this subspace W, the weights in the linear combination, where we have Y is equal to C1V1 plus C2V2 all the way out to C of P, V of P, are given by where we have C of J is equal to Y dot Vj all over Vj dot Vj, where we have the subscripted value J to be a natural number. Okay, and we have for the given set which we just worked with, again we have an orthogonal set with these same 3 vectors, and I'm going to reapply these. And given this particular set, all right, again this is an orthogonal basis for R4, and it says here that we are to express the given vector y, okay, also another 4x1 matrix where we have -1, 1, 3, 4, and to express this vector as a linear combination of the above 3 vectors in W. Now, so just taking what we have here, all right, so you have for multiplying y and taking the dot product with each of v of 1 through v of 3. Okay, and we have for the dot product between y and v of 1, okay, the result comes out to 10. And we have for what we have in the case of the dot product between y and v of 2, just kind of cutting to the chase, all right, the dot product ends up at 9. And for y in v of 3, again, if I take the transverse of y multiplied by the corresponding portions or elements in v of 3, the dot product would end up at 26. Now, in terms of expressing as a linear combination, as we get nearer, now we have for the dot products of each of the vectors in the subspace with themselves. Okay, we have the dot product between v1 and itself comes out to 23, and we have between v2 and itself, the dot product we have at 35, and we have between v of 3 and itself we have at 122. And in the case of what we have in terms of expressing as linear combinations, okay, so again we have y at c1v1 plus c2v2 plus c of 3 v of 3, and taking again what we have from the formula regarding combinations. Okay, we had the c of j. All right, so we have for the changeover in terms of the dot products. Okay, we have y1 v1 over v1 dot v1 v1, and so on and so forth, and just filling in the numbers that we had attained earlier. Okay, I had like y dot v1 was 10, v1 dot v1 was at 23, and so we have 10 23rds of v1, and following through likewise. Okay, have 9 35ths of v of 2, and we have for the third set we have 26 over 122 v of 3, and we have in simplified form we have 10 23rds of v1 plus 9 35ths of v2 plus 13 over 61 v of 3.